In this video, we're going to talk about this geometry problem that I've been wanting to solve for a while. So basically we have a semicircle that's inscribed inside a trapezoid. The parallel sides of the trapezoid are 5 units and 1 unit long. Can you solve the area of the semicircle? In case you want to solve on your own first, then feel free to pause the video. Let C be the center of the semicircle. Let D be the point of tangency of the semicircle and the trapezoid. Label the vertices of the trapezoid as A, B, E, and F. Next, from center C of the semicircle, draw the radius to point D. Let R be the radius of the semicircle. Since all radius of a circle are congruent, then segment FC must have a length of R because it is also a radius. Same thing with segment CE. The length is R because it is a radius. Keep in mind that there's always a radius that is perpendicular to the tangent line of a circle. Note that sides AF, AB, and BE of the quadrilateral are all tangents to the semicircle. Therefore, CD is perpendicular to AB, CF is perpendicular to AF, and CE is perpendicular to BE. Next, we're going to use the intersecting tangents theorem. According to this theorem, two tangents of the same circle that intersect externally have equal lengths. Therefore, AD is 5 units long, and BD is 1 unit long. Next, I'm going to draw a line from point A all the way to point C. Now I want to ask you this. Have you noticed anything? Anyway, you should have noticed that line AC produces two congruent triangles, triangle AFC and triangle ADC. Notice how these triangles have the same side lengths, which makes them congruent triangles. And what do we know about congruent triangles? Exactly. They have congruent corresponding angles as well. This means that angle FCA is congruent to angle DCA. I'm going to call these angles as alpha. And then the same thing happens when we draw the segment BC. This line forms another two congruent triangles, hence giving us two more congruent angles. This time I'm going to call the angles as beta. Next, I'd like to add all these angles here. As you can see, 2 alphas and 2 betas altogether form a straight line. Therefore, 2 alpha plus 2 beta is equal to 180. Divide both sides by 2, and the equation becomes alpha plus beta equals 90. Since the sum of alpha and beta is 90, we can say that angle ACB is a right angle. And also triangle ACB is a right triangle. We're getting close now. All right, for the next step, we will use the geometric mean altitude theorem. The theorem explains that the square of the length of altitude to the hypotenuse is equal to the product of the segments of the hypotenuse. Applying this concept to our problem, the radius CD is the altitude to the hypotenuse, and it divides the hypotenuse into 2 segments measuring 5 units and 1 unit long. Following the formula, the square of radius r is equal to the product 5 times 1. Obviously 5 times 1 is 5, hence r squared is equal to 5. And for the final step, we can now solve for the area of the semicircle. The area is 1/2 times pi times radius squared. The value of radius squared is 5. So the area is 5 pi over 2. Thanks for watching and see you next time.